Okay, so today what we're going to do is we're going to talk about the formation of ions, or forming ions from atoms. Atoms form ions, which are charged atoms, by either losing electrons to or taking electrons from another atom. Let's take, for instance, sodium. Sodium has 11 electrons. It has an electron configuration of 1s2, 2s2, 2p6, 3s1. Now, what this means is that sodium has one valence electron. It's the valence electron is the electron in the highest occupied energy level, so it has one valence electron. Below that is a full valence shell. So what sodium's going to want to do is it's going to want to lose that one valence electron so that it obtains a full valence shell S2p6 configuration. So when we take that electron out, you can see that the full valence shell is now the highest occupied energy level. So I'm going to go ahead and circle that. Now, we can represent this using a diagram of different orbits, which are the energy levels, and show the electron leaving, and that outer energy level that had the one electron is gone. So now we have what is known as a sodium plus one ion. The charge is calculated by taking the number of protons and subtracting the number of electrons. In this case, plus 1 equals 11 minus 10. Let's take a look at magnesium. Magnesium has the electron configuration 1s2, 2s2, 2p6, 3s2. So it has two valence electrons. Again, below energy level 3, there is a fully occupied valence shell, or a full valence shell, the s2p6 configuration. So magnesium is going to want to lose two electrons, its two valence electrons, and so that it obtains the full valence shell. Again, we could show this using orbital Bohr diagrams, where we're going to take our magnesium atom, which has the two electrons in the outermost ring, those are our valence electrons, and we're going to take those away. So we're just going to draw those leaving, and that leaves us with our magnesium 2 plus ion, which again has a full outer energy level. The charge of the ion is the number of protons minus the number of electrons, which in this case is 12 minus 10. Now, we could do this for every atom, but there's a pattern in the periodic table. Because the periodic table is based off of electron configuration, we can know how many valence electrons are in each column, and therefore the charge that each column will form. In the first column, we have an S1 configuration for the last term. It has one valence electron, so the charge will always be plus 1 for everything in the first column. In the second column, it's an S2 configuration, so it's got two valence electrons and a plus 2 charge. So we're going to skip over the whole transition metals section here. In the third column, which is boron's column, it's got an S2p1 configuration, which means it has three valence electrons and therefore forms a plus 3 charge. Now these are the positively charged ions. Everything in these columns will have either a plus 1 in the first column, plus 2 in the second column, or a plus 3 charge in this third column. Now, we're going to skip the fourth column here for a second. We're going to focus on the negative ions, or the anions. Let's take a look at fluorine. Fluorine has 7 valence electrons. It's got 9 total electrons, but it's got 7 valence electrons. And you can see that it is 1 electron short of a full valence shell. So what we're going to do is we're going to add an electron in to complete the valence shell. Give it that S2p6 configuration, or a full valence shell. So what this means is that fluorine is gaining an electron. Remember, on the other ones we were losing electrons, but fluorine is gaining an electron, or taking an electron from another atom. So fluorine will have a charge of -1. Remember, charge is the number of protons minus the number of electrons, which in this case here would be 9 protons minus 10 electrons, which gives us our -1 charge. If we take a look at oxygen, oxygen is 2 electrons short of a full valence shell. As you can see on the picture here, there are 2 electrons that we need to add in. So when we make our oxygen ion, what we do is we gain 2 electrons. We put 2 electrons in. That again will give us our full valence shell. Now, in this case here, since we're gaining 2 electrons, what we're going to do is we're going to have a charge of -2. The oxygen atom, which has a total of 8 electrons, is just oxygen, no charge, it's a neutral atom. But the oxygen ion, the oxide, is a -2. And again, that's because charge equals number of protons minus number of electrons, which in this case here is 8 minus 10, which gives us our -2. So going back to the periodic table, we can see the pattern that is developing here. For fluorine's column, it's an S2P5 configuration for the neutral atom, which means it has 7 valence electrons. It's going to need to gain 1, so it's going to become a -1 charge. For oxygens, it's an S2P4, so it's going to need to gain 2, so it's going to become -2. For nitrogen's column, it's an S2P3, which means it has 5 valence electrons, so it's going to need to gain 3. So it has a -3 charge. Now the noble gases, which are the column I just circled, have your full valence shell. Electrons are being exchanged to fill valence shells. We're either losing or we're gaining electrons for our valence shell. So what we have here is an S2P6 configuration, which means it has 8 valence electrons, which is the magic number, so no charge is formed. That leaves us carbon's column. Carbon's column has an S2P2 configuration, which means it has 4 valence electrons. And with 4 valence electrons, since the magic number is to get to 8, it can either gain electrons to get to 8, or it can lose its 4 valence electrons. So it needs to gain 4 or lose 4. Let's take a look at this from an electron configuration perspective. You can see that the carbon atom has 4 total valence electrons. Now, going to atom A, we're gaining 4 electrons. What this does is this fills our valence shell, gives us 8 valence electrons, but we needed to gain 4 electrons to get there, so it has a -4 charge. Remember, protons minus electrons equals our charge. Charge equals protons minus electrons. So we have 6 protons minus 4 electrons, minus 10 electrons gives us a charge of -4. Now we could also, going to atom B, lose our electrons. And in losing the electrons, we would end up with a carbon with a +4 charge. So the +4 charge is because we have 6 protons minus 2 electrons, which gives us +4. So looking back over here, you can see how the pattern for the charge is set up in the periodic table. And it's important to learn the pattern in the periodic table. The electron configuration, the valence electron, and the charge all have very simple patterns that are easy to follow and understand. And if you learn this pattern in the periodic table, you can easily predict the charge of any ion that will form in the periodic table, at least this section of the periodic table, until we get into more complicated stuff.